Hi everybody, in this video I'm going to go through question number 5 from the 2007 AP exam. So we're working with a table of values here. The setup is that we have a volume of a spherical hot air balloon expands as the air inside the balloon is heated. We have a function r to represent the radius. It tells us the graph of r is concave down. And then in the table, here we have to be careful. They're not giving us values of r. They're giving us values of r prime of t, so the rate of change of the radius over the given interval. And then we've got kind of an initial condition here. The radius is 30 feet when t equals 5. So now they're asking us to estimate the radius when t equals 5.4 using the tangent line approximation at time t equals 5. And then we have to determine is our estimate greater than or less than the true value. So if I need to use a tangent line approximation, I know I'm going to need two things. I'm going to need a point, and I'm going to need the slope of my tangent line. So we're doing this at time t equals 5. So when time t equals 5, I know they told me the radius is 30 when t equals 5. So there they were giving us our point. For my slope, well, my slope is going to be r prime of 5, which I can get from the table right here. And so I know my slope is 2. So using that, I can write the equation of my tangent line. So I'm going to use the variables that are in the problem. I have r minus 30 equals 2 times t minus 5. And I can rearrange that to be 30 plus 2 times t minus 5. So now I want to estimate the radius when t is 5.4. So now r of 5.4 is going to be approximate, right? Because we're using that tangent line. So for t, I'm going to substitute 5.4. So I'm going to have 30 plus 2 times 5.4 minus 5. So all I was doing there was for my t, I was just substituting in the 5.4. So now we can simplify that. We get 30 plus 2 times 0.4, which is just going to be 30.8. And the units on the radius is measured in feet. So now there's our approximation, is 30.8 feet. Now we have to determine, is our estimate greater than or less than the true value? So here's what we need to know about actually here, that the function, the graph of r is concave down. If the graph of r is concave down, that means this tangent line is sitting above that graph, which means our estimate is greater than the true value. So we would say the estimate is greater than, sorry about my messy writing, greater than the true value because the graph of r is concave down. And so for this one, this was worth 2 points. So 1 for our approximation, and then 1 for determining if it was greater than or less than. All right. Part B says find the rate of change of the volume of the balloon with respect to time when t equals 5, indicate units of measure. Now, again, hopefully these keywords are giving you a clue as to what to do here. When it says find the rate of change of the volume with respect to time, that's telling us that this is a related rates problem. So the rate of change of the volume with respect to time. Well, this problem gave us an equation for the volume, And it says volume is 4/3 pi r cubed. Now in this case, it gave you the volume. I would not expect that to always be the case, so I would make a note about this somewhere. You should know this formula. So since it's related rates, I have to find the rate of change with respect to time. I'm going to differentiate with respect to time. So dv dt. On this side, I'm going to multiply by 3. I get 4 pi r squared dr dt. So now it looks like I've got 3 quantities here. I've got r, dr dt, and dv dt. Now they're asking us to find the rate of change of the volume with respect to time. That means dv dt is our unknown. So hopefully I know these other values. Well, r and dr dt, we actually know and we use them above. At time t equals 5, we knew the radius was 30. And using our table, we had found that at time t equals 5 here, our rate of change was 2. That was our dr dt. So now we can just substitute what we know. This is still unknown. We have 4 pi times 30 squared times 2. And then if we put that into our calculators, we would get 7,200 pi, and that would be cubic feet per minute. And so for this one, they gave 2 points for that formula for the derivative there with respect to time, and then 1 point for the answer. All right, part C now says use a right Riemann sum with the 5 subintervals indicated by the data in the table to approximate this integral. So let's go ahead and set that up. So I have 5 subintervals. So from 0 to 2, 2 to 5, 5 to 7, 7 to 11, and 11 to 12. And I'm using a right Riemann sum. So 2, that's 4, 5 is 2, 7 is 1.2, 11 is 0.6, and at 12, I've got 0.5. So this integral 0 to 12 of r prime of t dt is approximately 2 times 4 plus 3 times 2 plus 2 times 1.2 plus 4 times 0.6 plus 1 times 0.5. And if we put that in our calculator, whoops, I made an error. Whoops. All right, try that again. So 8 plus 6, 2.4 plus 5. There we go. We should get, hopefully if I added everything up, we should get 19.3. Again, if we think about our units here, I want to get purple. Whoops. There we go. Our units here were minutes, and then we had times feet per minute. So when we multiply those out, the units on our answer then should be feet. So 19.3 feet is the approximation. And now I have to explain the meaning of that integral. Well, if I integrate from 0 to 12, I'm integrating the rate of change of the radius. When I integrate that rate, I should just get the change in the radius. So this integral represents the change in the radius. And we put the units, so measured in feet over the time interval t equals 0 to t equals 12 minutes. Now, if we were referencing our value, we would say, right, the approximate change in the radius, or the radius increased by approximately 19.3 feet over that period of time. The idea is that integrating the rate gives you the change in that amount. And for points on this one, I don't know why it's doing that, sorry. There we go. For the points on this one was 1 point here, and then 1 point for explaining the meaning. All right, last part here. Oops. Is your approximation in part C greater than or less than the actual value of the integral? So here's what we have to think about. With a right Riemann sum, we know that answer is going to depend on whether the function was increasing or decreasing. Now, the only problem we have here is we don't know whether r is increasing or decreasing. What we know is the graph of r is concave down. And I have to think about, well, what does that tell me about r prime? So here's what I know. If you think about what we know about graphs of derivatives, I know by looking at the derivative, if I'm looking at a graph of r prime, I know it's concave down wherever r prime has a negative slope. So if r is concave down, means r prime has a negative slope. And if r prime has a negative slope, it means r prime is decreasing. So that's kind of the logic we have to use here. Now, if I know that r prime is decreasing, so I have a decreasing function, and I used, let's see, a right Riemann sum. So I used that right endpoint to determine the height of my rectangle. It means this was an underestimate. So that means the approximation is less than the actual value of this integral because r prime is decreasing and a right Riemann sum is used. All right, so for that one then, it was, I think, really just 1 point for being able, to explain this. Now, if you were counting at the points, a typical FRQ is worth 9 points. What they did here is they gave +1 for correct units in parts B and C. All right, that's it for this question.